All right, so today we're going to be talking about double time and half-life. So our learning target today will be how I calculate remaining amounts of material or substance using double time and half-life formulas. The first topic we're going to touch on is half-life, which is the amount of time that's required for a quantity to decay to half its initial amount or size. So you take a whole item, you cut it in half again, and continue on and on and on. So let's talk about the formula and what each part means. So in subset T, this is just the amount that's remaining, like the amount that's left after you've done the figuring and the work. So this is just the amount remaining. Okay, and then let's talk about in subset 0. This is your initial amount. What was the amount that you had to start off with? The initial amount. And then we're going to have T. This T is going to be the total amount of time that you're being allowed or given. So T is for time. And we're going to say total time. And then we're going to have half-life, which is H. And this half-life, let me write this down. So it's half-life. And they're going to usually give you a specific amount of how often that half-life occurs. Like half-life occurs every 30 minutes or a certain amount of time. So I'm going to kind of mention it's half-life time. It's very specific to how often that half-life occurs. Okay, so here we have a graph of iodine 131 and its half-life. You can kind of see how it's, going down and to the right, and the quantity is decreasing as time increases. So by looking at this, we're going to refer back to, on the table, we're going to fill out this table about the percentage remaining. So if I have all of my quantity, then I have 100% and I have 0 half-lives. 1 half-life would be 50%. 2 half-lives would be half of 50, and that would give us, 25%? This is all in percents. And then half of 25 would be just 12.5. And you take half of that or divide that by 2, and now we've got 6.25. Continuing on, we have 3.125. You can easily put this in your calculator, take the value, divide it by 2, and then we have 1.5625. And then finally 0.78125, 0.78125. All right, so example 2, if you start with 500 grams of radioactive material and the half-life is 30 minutes, how much do you have after 80 minutes? First thing I'm going to do is go back into the word problem and underline anything that's important to me. So if you start with 500 grams, that would be considered our initial amount. So I'm going to go over and underline it and put it where the initial amount goes, which is our in subset 0. I know that is 500. And then it talks about the half-life is 30 minutes, so half-life is 30 minutes. Then I'm going to go over and put 30 for my half-life. And it tells you the amount of time that they're giving. They want to see what happens after 80 minutes. So 80 would be our time. And we're looking to find the amount left after, so the amount remaining. All right, so next I went ahead and set up the formula so you can see where everything goes, and I kind of color coded it so make it a little bit easier. We have 500 times the 1/2 to the 80 divided by 30 power. So I went ahead and plugged in the formula into Desmos on my phone so you can kind of see what it looks like, since that's what a lot of you are using anyway. And you can see that the total is 78.745, and it continues on. So for my answer, I know it's 78.745. And if I wanted to round it to the nearest tenth, then I would have 78.7 grams remaining. And that is your N subset T, your total remaining after the half-life. All right, so let's talk about double time. Double time is the amount of time it's required for a quantity to double its initial amount or size. So we're just going to talk about the formula real quick that we're going to use. A lot of it's very similar to the half-life, the N subset T. This is going to be your total amount remaining, so we're going to have total amount. And then we're going to have the N subset 0. Now, just like before, this is going to be your initial amount, what you start with. So initial amount. And then we have the 2 as our base. And then we have T again. How much time? And this will be time total. And then we'll have D, and instead of half-life, this is going to represent the double time. So the amount of time it takes for something to double. So it'll tell you the double time is blank, and it'll give you a value, and that's kind of where that would go. Okay, so on example number 3, we're going to talk about doubling time of bacteria. So in this situation, we're going to suppose that the number of bacteria in a petri dish doubles every 3 minutes. So it's doubling every 3 minutes, meaning that's the value that we're going to put in for D. So D would equal 3. And then it mentions there were 4 bacteria when it started. So that would be our initial amount. So 4 bacteria will be our initial amount, which is in subset 0. And then the question is asking us how many bacteria would there be after blank amount of time. So obviously T is going to be changing based on the 5 different questions that's listed in the box. So we'll do each one by one, and we're going to put, so this value in the T blank will change. So let's get started with filling out our formula. We obviously don't have the total amount, but we do have an initial amount. The initial amount is 4. So we have 4, and then we have our parentheses. I like to put the 2 in parentheses, close parentheses. So 4 times 2 to the T over D amount. So T, we're going to start with A. So we'll make that 6 over the double time. It says the double time occurs every 3 minutes. So that would be 3. And we're going to see what that equals. And go plug that into your calculator. You can use Desmos or a regular calculator. I think for me, I'm going to go ahead and just do it by hand. I know that 6 divided by 3, that would give me 4 times 2 to the 2nd power. And then I know that when I square something, I'm going to take 2 and square it. That is going to give me 4 times 4, because 2 squared is 4, and that would equal 16. So my total for A would be 16 bacteria. All right, so we're going to continue that same process over and over again, especially for B and C. Pause now. And then now we're back, and the answer for B, you should have gotten for 9 minutes, you would have had 32 bacteria. After 15 minutes, you should have had 128 bacteria. All right, so on the next answer for D, it's referring to, it gives you 1 hour. 1 hour is not in minutes, so we are going to need to convert 1 hour to minutes. And we know 1 hour will equal 60 minutes. And so you need to input that value where you did the 6, 9, and 15. So when you plug that in, your answer should have been 4194304, and that would give you 4,194,304 bacteria. And then the next one is talking about days. So again, we need to convert 1 day into minutes. So we know that 1 day equals 24 hours. And then to get minutes, we would take that and multiply that by 60 minutes per hour. and we know that equals 1,440 minutes. Plug that in, and then you're going to end up getting a very large number, but we're going to write it using our scientific notation. So we're going to have 1.25. I'm going to round it to the nearest tenth. 1.25 times 10 to the 145th power. That's huge. So a lot can happen in just 24 hours. Okay, so on this particular part of the question, it's just a continuation of before. So we still have the initial amount, which is our n subset 0 is 4, because that's the amount of bacteria that we started with. So as far as our formula is concerned, we already know that that will be 4. And then we're going to have open parentheses our 2. And then we have our time divided by our double life, and we know that our double life is going to be 3. That is not going to change. And then in our formula, we do have the total amounts. They're giving us the total amounts and want to know what time is. So we're going to kind of work backwards to do this. So from here, I'm going to go ahead and let's focus on F, meaning that we're going to do 16 bacteria. So that means my total will be 16. I'm going to plug in 16 here. And I am looking to find our time because I don't know what that is. Now, to get up to the T, it's in our exponent position. I need to isolate that base of 2 so that I can then get to the T in the exponent spot. So to do that, I'm going to have to divide both sides by whatever's being multiplied to the 2, that base 2, and that it would be our 4. So we're going to divide both sides by 4. And then the 4 becomes a 1. The 16 over 4 will then become 4. And I'm going to rewrite our problem. So now we have 4 equals 2 to the T divided by 3 power. All right, so on our next part, we are going to want to have our bases be the same. So I'm looking to see, can I rewrite this 4 to where I can have a base of 2 so it matches the one that I have on the right? And I can do that. So I'm going to say if I write a 2 as my base, 2 to the what power would give me 4? And I know that 2 to the second power is the same as 4. And then I know that can equal, I'm going to set that equal to our given, which is 2 to the T over 3 power. Now my bases are the same. So my bases, I'm going to kind of mark through those and ignore them. I'm going to focus on the exponents. I'm going to set those equal to each other. So now I'm going to just focus on this part here. I'm going to go off to the side and write it. So I have 2 now equals T over 3. I need to solve for T. You might recognize this. If I put 2 over 1, I can then cross multiply, and that would give me T equals 6. So that's how long it would take. It would take 6 minutes to have 16 bacteria, and that would be the answer for F. All right, so I'm going to do another example. So I'm going to move this one out of the way to kind of have more room, and we'll do the G for 64 bacteria, setting it up the exact same way. So plugging everything into our formula, our total is going to be 64 this time. So we have 64 equals the initial amount of 4, open parentheses 2. We don't know the T value over D, which was 3. So again, you're going to do the same thing as you did before. You're going to divide both sides by that 4 out in front of the 2. So divide both sides by 4. The 64 and 4. 64 is going to be 16. So we have 16 now equals 2 to the T over 3 power. Again, you want to get like bases. So I need to take and make the 16 have a base of 2. And the only way to do that, if I make the base be 2, I then need to ask myself, 2 to the what power would give me 16? I know 2 to the third power is 8. So we would say 2 to the fourth power would be 16, which now equals, I'm going to just bring down the other side, and you have 2 to the t over 3. Again, we're going to get, now that our bases are the same, we're going to set our exponents equal to each other. So we have 4 equals t over 3. Make the 4 a fraction, and now you can cross multiply. So we now have t equals 12. So the time it would take to get 64 bacteria would be 12 minutes. All right, so that was G, and we're gonna make this a little bit smaller and move it out of the way so I have room to do the next one, and we'll focus on H for the 200 bacteria. So we're gonna do the exact same thing again. We're gonna set everything up. I'm gonna do a different color so it stands out. So now we're gonna do 200 equals 4 times 2 to the t over 3 power. Same thing applies. We're going to divide both sides by 4. And that's going to give me 200 divided by 4 is 50, which equals 2 to the t to the 3rd power, or t over 3 power. So at this point, I would approach this problem one of two ways. If you were to look to see if you had a base of, if you could make 50 a base of 2, you cannot. So there's a couple of different ways. I would think maybe the easiest way is to go into your calculator or into Desmos, and you can create 2 equations. So what you're going to do is you're going to take, for the 50, you'll type in y equals 50. And then for 2 to the t divided by 3 power, you're going to do the same thing. You're going to go into Desmos, and on another line, you're going to put y equals 2 to the t divided by 3 power. And what you're going to do is you're going to take and look at where those 2 lines intersect on the graph, and that will give you your value for t. The other way would be to move the 50 over if you wanted and rewrite the equation as y equals 2 to the t divided by 3 power. Move 50 over and you have minus 50. And then you could go and look at your table and go see approximately where that answer lies. So I did the 2 intersections, and I found that t is going to be approximately 17 minutes. It was 16.932. I just rounded up and got my 17 minutes. Okay, so in example 4, it talks about a substance that decreases from 150 grams to 100 grams in 10 minutes. What is the half-life of this substance in minutes? So we're going to go and now find half-life. The initial amount, if it started at 150, that was going to be our initial amount. Our end value was 100, so I'm going to put 100 for the total, because that's what we ended up with. It says the time, it took 10 minutes, so that would be our time, would be 10. And now we're looking to find out H. So I'm going to go ahead and set up the problem now. So here's our problem set up. We have 100 equals 150 times 1/2 to the 10 divided by H exponent. So I would go ahead and isolate the exponent base as much as I can. I would divide both sides by 150 to at least get it into some simpler forms. And that means that we'll have 10 over 150, or 100 over 150 simplifies down to 10 over 15, which then gives us 2 over 3, because 5 goes into 10 twice and 5 goes into 15 3 times, equals 1/2 to the 10 divided by H. To solve for H, I would go back in and I would go into Desmos and type y equals 2/3 and y equals the 1/2 to the 10 over, and I would put x, and then I would see where those 2 intersect to get my answer. Okay, so once you plug that in and go look at Desmos, you can tell that x is going to be approximately, or our H for our half-life, approximately 17 minutes.